Okay, in this video we are going to implement some of the feature extraction techniques, and we'll be building pipelines that we have learned in this in different occasions in this course. So let's go through different pipelines that are available in scikit-learn. We'll be focusing on PCA, multidimensional scaling, kernel PCA, isomap, locally linear embedding, Laplacian eigenmaps, which is named as spectral embedding. We will also be seeing one other very recent kind of technique called t-SNE, which is really powerful, again, neighborhood-based dimensionality reduction technique. So all these techniques, although they are unsupervised, we can make them supervised by first deploying a feature selector, and then that is one way. Or we can go to simply a linear discriminant analysis if you really want. That is also available in scikit-learn. So let's start. Pandas as PD. We have to import certain packages. NumPy as NP. Then we have to import PCA. We have already implemented PCA from scratch, but let's see the support of PCA available in scikit-learn, sklearn.d decomposition. From there, import PCA. That is the built-in PCA or available in scikit-learn. Then we have this kernel PCA as well. So let's copy and paste. Here we have kernel PCA. Yeah, that's available. Then we have multidimensional scaling if we really want, from sklearn.manifold import MDS. Yeah, import that. And then we can have several other nonlinear dimensionality reduction techniques. All they belong to manifolds and local neighborhood. So MDS, then we can have isomap if we want. Then we can have, for example, locally linear embedding. Yeah, LLE, very famous. Then we can have spectral embedding. Spectral embedding, by the way, this is the name of Laplacian eigenmaps. Yeah, so that's available. And then we have, for example, t-SNE that we have not studied in our course, but that is kind of a local neighborhood based dimensionality reduction method and is really famous. So let's focus on these, although other than PC and kernel PCA, all of these are really, really slow, and it may take maybe, several minutes or maybe a couple of hours to return depending upon the size of the data set. But let's just try to run a few of those and get comfortable with. So what next, what we have, let's say we have from sklearn.feature selection. Let's have our import of select k-best just for making a pipeline if you really want. And then we may have from sklearn.pipeline, pipeline import make pipeline. Yeah. So last but not the least, if there are certain warnings that you do not want to appear, just press them, right? Warnings dot filter warnings ignore. In case if you really what's that? So yeah, so all the packages, required packages have been imported. Now this is the time to import our data. So let's import our data, which is here, swarm behavior data that we have encountered earlier as well. Yeah, so let's read this data and apply some of our concepts that we have studied so far on this data. So df is equal to pd.read CSV, read CSV. This is for raw string, and just copy and paste, and that's it. It may take a little while, although the original data was having a lot of records. I have reduced this data. So now if you see some of the look on this data, this is the data. I mean, I have just seen the 5 records of it. It has 2,401 columns. In my previous example, I have used the same data in feature selection module as well. Accidentally, when I was actually reducing the data, reducing the rows, an unnamed column was added here, and in that video you might be seeing there are 2402 columns. Actually, accidentally one column was just added here, unnamed column. So in that video you might have encountered that the total number of columns are one more than the one that appear here, but there was one column was just mistakenly added. You can consider that column as garbage. So I have fixed the file now. So this is the file with that's a classification data set, swarm behavior data set, with this as the class label. That's a binary classification data set. So let's pull up the labels y, which is df.class, and x, the data, which is df.drop, class x is equals 1. So yeah, so that's x.shape. Now you can see we have, by the way, the data is represented here in transformed way. So normally in whole hour lectures, the first value was dimension and the second value was the total number of points. The way scikit-learn receives the data is completely in transformed way. So we have to represent in the following way. This is n, the total number of samples, and this is the dimension. So the dimensionality of the data is 2400. That's the restriction of scikit-learn. It receives the data in this form rather than the transformed form that we have explained in the video. But that's fine. That's not a big deal. So let's first fit PCA model in our data. So for example, PCA is equal to PCA, and then n components is equal to, if you give, for example, components 10, what it will do is it will reduce these 2400 dimensions to straightforward to 10 dimensions. I will tell you later on how can we fix that. So x PCA is equal to PCA.fit, that is x, and then we can have so that's the model, PCA model maybe, yeah. So that's fit model. That's so you fit that in x, and that is your PCA again, PCA.fit. So we can have this PCA.fit, and then we can have the following PCA.transform, which is which actually transforms this x to x new, and we can now see the dimensionality of this x new. Yeah, so the dimensionality of this x new dot shape, as you can see, is it reduces to 10 dimensions, but you do not know whether 10 is a good number or not. So the built-in support of PCA also gives you liberty to actually describe this number of components in a floating point number between 0 and 1, for example 0.95, and that basically tells the PCA to keep 95% of the variance or information, as we discussed in our own implementation of PCA as well. So here, let's see how many dimensions do we need to implement this kernel PCA, to implement to get the 95% of the information. Yeah, so let's see, x new dot shape, So only 5. Oh my God, only 5. So if you want to keep 95% of the information, you only need 5 dimensions. Huge. I mean, huge reduction in dimensions. Yeah, so there are a couple of other parameters as well. If you want to see those, if you want to see full documentation, you can just type a question mark, shift enter, and the documentation will open up in front of you along with the examples and stuff like so, if you really want. There are a lot of other parameters as well that you want to tune with. Okay, next we implement Kernel PCA, which is again like everything is just like the same thing, but let's just implement the Kernel PCA. So see one theme. You have the model, whatever the model is, whether it is MDS or Kernel PCA or whatever. You have your model. Then you call a fit function. Then you call a transform function, and you are done. That's it. That's the that's the way it is. So for example, kernel KPCA is basically kernel PCA. You can define the kernel. There are several kernels. One famous kernel is RBF. That's a Gaussian kernel. You can define the number of components. That is, let's say I want to reduce to again 10 components using this kernel PCA. And there is a gamma parameter for RBF kernel. Let's say that is none. So that's your model. Now what you do is kpca.fit x, and then what you do is x new is kpca.transform. That's it. It will take a while because the data is huge and this RBF kernel will take time. So let's wait for it. Let's wait for this direct to go. Yeah, so let's see. Let's count and see when it returns. Let's count, for example, 1, 2, 3, 4, 5, 6, 7, 8. No, it is not returning. I mean, it's taking time. And not only this, I mean, when you will move to these techniques that are neighborhood techniques, they will take, I mean, a lot of time. Yeah, so you call that function and then you just go away and come after some couple of hours depending upon how big your data is. Yeah, fortunately this has returned because it has closed form solutions, but this normally is not the case for the techniques that I've shown you above. So shape, so that is 10. Yeah, great. Now what we do, because these techniques, MDS, isomap, locally linear embedding, all these techniques, they are really time consuming. The game is again same. For example, let me show you an experiment how slow these techniques are. Let me give you an example of isomap, for example. And we will wait, for example, for a couple of minutes and see what happens. So yeah, so again, we have, let's say, isomap model. Isomap is equal to isomap, and we have number of components is equal to, let's say we want to reduce to 10 components. Then what we have is isomap.fit. That protocol is same, very simple. X new is maybe X new is let's say X new is isomap.transform X. So yeah, it is going to take time. And not only this, isomap, all these techniques, they are hilariously slow. They build k nearest neighbor graphs, they build kernel matrix, and I mean this k nearest neighbor graph building and transformation and all that stuff. It takes a lot of time, particularly if the data and dimensions are huge. So it is going to take a lot of time. Believe me, I will share this file with you and you can then go and check that it indeed takes a lot of time. So I'm going to interrupt the kernel just to return back to the notebook, because it is not going to return very soon, I know. Yeah. Yeah, the kernel should be interrupted now. Come on, kernel, get interrupted, get back. I want to work more. So what should we do? Yeah. So what can we do here? Oh, come on, kernel, come back. Why are you not getting interrupted? I don't know. It is not returning. Let's wait. Maybe the interruption is also taking time. That's a bad news, but that's what is happening. And this is generally the problem with all these methods: multidimensional scaling, isomap, locally linear embeddings, Laplacian eigenmaps, t-SNE, and several other methods. All the methods that are local neighborhood methods, and they rely on k nearest neighbor graphs. That's a problem with all of these. Yeah, it is not returning. What should I do? Should I shut down it? And what should I do? Shut down. Okay. Leave. Okay. Let me import that file again. Feature extraction. That was the file, I guess, if I have saved that file. Yeah. So that's the file. And this was the bottleneck. Yeah. However, what we can do is we can make pipelines. For example, let me make a pipeline. Let me first run all of these so that just reload the data. I have interrupted the kernel, so shape and PC and stuff like so. What I can do is I can make pipelines. For example, Alt Enter, that will make another cell. What I can do is I can make pipelines where first we can, for example, apply this feature selection method, which is really fast, using this filter method, and then we can apply some other method like PCA or kernel PCA, which one aspect of that is it brings supervision to our dimensionality reduction technique, because the current data is classification data. And second, it will make the process very, very fast, particularly for the neighborhood dimensionality reduction methods. So we already have imported make pipeline and select k-best. Let me give you a flavor of that. Let's say our model is make pipeline, and we first have to show which method we want to use first. So first we want to use select k-best with, let's say the value of k is let's say 10. We want to select the best 10 features, and then after that, after selecting the best 10 features, I mean reducing the dimension to 10, then I want to apply a PCA model on that, where I need to hold the number of components, let's say equals to 2. So let's say I want to reduce my dimension eventually to 2, but what I really do is I first reduce the dimension to 10 using a filter method, and then I will give that result to PCA, which will take original dimension as 10, and then it will reduce to 2 using this PCA model. So that is my model, that's my pipeline. I can make the pipeline further lengthier. Then what I do is mdl.fit xy, that's fit, and then we can have x new, which is mdl.transform. Just the way we call the transform on PCA and fit function, just the way we call it on kernel PCA and even it on MDS and isomap and all these kind of concepts. So let's see how it works. I'm pressing Alt Enter so that I get a cell down. So it will first, oh, it is that fast. Oh my God. It has selected 10 features and then it apply PCA and get the best 2 features. Let's see, X new shape. That is this. Yeah, great. Let me have this model for t-SNE. Let me see whether t-SNE can help me or not. Rather than writing PCA here, let me write t-SNE. That's a neighborhood-based dimensionality reduction technique. But here my hope is that it will return quicker because we first have filtered our data. The significant amount of dimensionality reduction has been done by select k-best, and then a t-SNE is applied on that. We can apply isomap, locally linear embedding, whatever here, and the hope is it will run a little faster than expected, than as compared to if we have not applied this pipeline earlier. So let's wait and see how much time will it take. Let's see. The expectation is it should take just a few minutes and it should return back to us. Let's see what it does. Come on, return back. It's taking a lot of time. Yes, now see, we already have reduced our dimensions to 10 and then we apply this t-SNE and it is still taking some time. Think about applying these kind of methods directly on high dimensional data. They are very slow. That's a problem for all neighborhood-based method techniques. That's a problem. They are slow. I mean, yeah. So let's wait for when it returns back to us. Yeah, let's not interrupt the kernel. Let's wait for it. I know it consumes our time, but let's wait for it. I'm doing the live coding. I don't have this model saved somewhere. Oh my God. Eventually it returns with an error. t-SNE object has no attribute transform. Oh my God. This t-SNE has a fit transform method. Oh, that's a bad thing. This t-SNE, it has fit transform method rather than simply transform. So why don't we use locally linear embedding here? All we have to do is to test the pipeline on some. So actually this t-SNE has fit transform method. It doesn't have transform method. It has fit transform method. Anyways, let's write this locally linear embedding. Maybe that helps us. Maybe that runs quickly. Maybe. Let's see. Finally. Yeah. Oh my God. It returns x new dot shape, and that is 6004 by 2. Forget about this performance if you do not have selected the features before. If you directly apply locally linear embedding, it is going to take much longer, much longer. Yeah, so let me just apply a few more techniques within the pipeline. Just to let's apply Laplacian eigenmaps. Let's apply spectral embedding, and let's hope it has a transform function as well. It should have. Yeah. So where is that? Yeah. So let's see how much time will it take, and after we will print x new dot shape, and let's see what happens. Yeah, even with the pipeline it may be taking a lot of time. Maybe like locally linear embedding, maybe it runs quickly. Yeah. Oh, I guess it doesn't have transform again. It has fit transform. That's a bad news. Yeah. Should we call fit transform? And will that work? I guess no. Why don't we try? Because this select k best method must also have this fit transform method. So But then we should not have this fit function. We should not apply this fit function. We should call directly fit transform. Yeah. Fit missing one requirement, optional Y. Yeah, so why don't I, rather than building this pipeline, why don't I show you that in a cascade style? Although if I write a Y here, maybe it should work. But let me show you with a customized pipeline or a cascade style. That may help. So let's see. If this doesn't work, then we will go to, rather than building this pipeline, we will apply select k-best first, and oh yeah, it works. Yeah. Now now this t-SNE will also work. Yeah. So sorry about that. I just want to show you that all these methods, they work. They're just available and they are that simple. Yeah, so let's see. t-SNE, Laplacian eigenmaps, locally linear embedding. You can apply the multidimensional scaling if you want. We have already applied PCA and kernel PCA and all that stuff. So where were we? We are here. Yeah, it is running. Let's wait for a few more moments. This will return back, and then I will stop the video. I will finish the video. I know I've made you I've made this video a lot boring because of these delays in this computational delays. But I guess that was important to show you that these methods, although they are very sophisticated, the neighborhood methods, but they are slow. And one problem, you might be thinking that why don't we apply kernel PCA, because at the end of the day they are all special cases of kernel PCA. Well, the problem is we do not know the appropriate kernel to use. Using RBF kernel is not always a good choice. So if we know a best kernel, it returns. If we know a best kernel, then go for kernel PCA. It is faster, but it is faster even if the kernel computation is simpler. If the kernel computation has problems, then the kernel PCA will eventually take that much time either way. So that returns, that's the result. So yeah, hope you understand these pipelines and feature extractions and all that stuff. With these pipelines, we can add here a feature scaler, for example, standard scaler, to scale the features, to make the average value 0, to center the features first, and then to scale the features between -1 and 1, for example. We can add all these components in this kind of pipeline that is called a standard scaler, for example. There are other scaling methodologies as well. And if we have several pre-processing steps, we can make a huge pipeline, and we then have one model, and we just have to call these two lines. We have to write these two lines, and we are just good to go. Yeah. So with this file, with this code, I guess you'll be having really good idea of how to work with these dimensionality reduction tools. Most of these we have studied. Actually, all of these we have studied. The one that we haven't studied is t-SNE. That is also very important. It's a beautiful tool, particularly for visualizations. And there's a tensor board in TensorFlow that actually uses beautiful kind of visualizations based on t-SNE, and there are comparisons of t-SNE with PC as well. Yeah, so with that, I finish this video. Hope to see you next time.